The 15th week. The exam is next week, is that right? The final? 37 pages of just fun. When is the exam? What day of the week? Monday. It's on the Monday. Any idea what time it is? 10:30, I think is traditional, isn't it? 10:30. Yeah? Make sure we're okay with that. I think I'm pretty sure it's 10:30. It usually is. So, what we need to do between now and the end of this week is to get finished with chapter 12. And as we mentioned last week, there is no new chemistry in 12. We've done all the chemistry you need to do for 12 and for the final. The final is comprehensive. The final attempts to bring out of you some idea of whether you understand what's been happening. Memorizing really doesn't work here. Understanding stuff will. What we're doing in chapter 12 really is talking about putting it all together. And we left off with these slides, which are kind of summaries of where we've been for the past 14 weeks. We started off kind of gentle. We did some structure. We did some descriptions of how organic chemicals look. And then we started to do some reactions. We did an awful lot of what we call functional group reactions, where we turned an alcohol into a bromide. We turned a bromide into an alkene. And then towards the end, we did some chain elongation using alkyne chemistry. We did carbon-carbon bond forming reactions. So use these types of slides as sort of guides to where we've been, so that as we work our way through this week, certainly in recitation and in class, we'll try and wrap things up, and we'll try to do, we'll try to do as much as we can to get you ready for the final. So what I want to make sure we're okay with here is the idea of the centrality of synthesis, the idea that we've been building to something. And 12 is the capstone part of this semester. We choose to stop here because it really does give you an idea of where we are. We need new compounds all the time, whether it be for curing a disease, whether it be for making a material to make something to go to the moon or to Mars or whatever. Organic synthesis is central to all of this. So new material is very, very important. You can't have your iPhones the size they are without organic synthesis, without materials chemistry. The idea of new medicines and pharmaceuticals, many of you are heading in that direction. Pretty much all of the drugs that are out there are synthetic, and so they've been made by chemists. So we'll deal with this sort of picture as we go through next semester, and we'll see the bigger picture, hopefully. What we need to do now is play the game. We need to start, apologies to the soccer players, but we're going to win. We're going to play this game using the basic rules. I'm going to put it together and do well next week. The planet gives us an awful lot of raw material to start with. We can get raw materials from plants. We can get them from crude oil. Chemical engineers down here, nice picture. Chemical plant, right? We can take materials that the planet gives us and purify them, distill them, crystallize them, and then use them to go further. And what you'll have to do this week, thinking about next Monday, is deal with this bit in the middle. Deal with this idea of what chemistry is all about from my perspective as a synthetic chemist. You need to design a route, whether you're making a pharmaceutical like ibuprofen, whether you're making materials for cosmetics, whether you're making lubricants for oil and the petroleum industry, or whether you're making plastics to put on the side of a house. You need to design your product. You know what you want to make, you need to go ahead and design it and then put it together. So we're going to talk about how to design a synthesis. When do we do what? A lot of people will say, okay, that's a bromination reaction, sure. And that's an elimination reaction, but when do you do what? When do you put it into the sequence that gets you the right answer? We'll do synthetic steps, obviously. A lot of what we've been building up to on the exams, give me the products of these reactions. Here are some reagents, give me the products. That's what we call a synthetic step. And on the exams and on the quizzes, people are getting better. Give me a product from each step. That's what I'm after. What we've done are two big jobs. We have done carbon-carbon bond forming reactions, and we have done functional group interconversions. That's been the whole story for this semester. There are a lot of reactions we've done. There are a lot more next term. We haven't really talked in this class, but you have in lab, about isolation. How do you get the product out of the reaction mixture? Maybe you distill it. Maybe you crystallize it. That's a really important part of doing synthesis. We can do purification by the same sort of techniques. And then next semester we'll see characterization. Nobody's asked this question yet. How do you know what happened? How do you know what the answer is? We'll see a lot of that next term when we do spectroscopy, and we talk about how scientists will work out the structure for sure of a product they've made. So this is the game. This is what we're going to do from now on until the end of term, and it also is a big part of 3720. So we started off thinking about simple ideas, simple concepts that you should be able to bring with you next week and put into practice. If you look at these two molecules, it's a dead giveaway. One is bigger than the other. There are more carbons on the molecule on the right than there are on the left. So you have to do some sort of carbon-carbon bond construction. And the only way we have to do this so far is to use alkyne chemistry. So that's easy. And that's pretty straightforward. If the molecule at the end is bigger, chances are it's a carbon-carbon bond forming reaction. So when we start to think about that, we think about chain extension or chain elongation. The simplest way to do this so far is through an SN2 reaction, in which you make the acetylide anion by deprotonation. You take a base and you take the proton off here and make the negative charge, very powerful nucleophile, and you put in the appropriate electrophile. You count the carbons that are missing in the product and you put in the electrophile that matches. And then we end up with a longer chain. Well, in this example, we don't want an alkyne. We have done the job to get to the bigger picture, to get to the bigger molecule, but we want to get rid of that triple bond. So what we have to do now is think about functional group interconversion. How do you turn the alkyne functional group into the alkane? And the answer obviously is reduction. So we add a lot of hydrogen gas, we add some platinum or palladium as a catalyst, and we get that product. So that's what all we're doing this week. We're going to add things together, we're going to move things around, we're going to do synthesis. Stop me as we go through here if you're not sure what's happening. It's pretty quick. I have 3 days to get through this, which is more than enough, and the more you practice at this, the better you will get. So we have to do things like move things around. We have to start taking a product that the planet gave us and turn it into something that we want, that the planet didn't give us, something new that we think will be useful. A lot of this will be focused on alkenes and alcohols and halides. So you think about what a halide is usually in a molecule for. It's in there to leave. So we'll use it to set up some sort of substitution reaction. You think about what alkynes did. Alkynes were able to knit things together by deprotonation followed by alkylation. Alkenes usually can add, and we can form alkenes by elimination. So what we'll see to start off with today is the sort of transposition of that bromide from there to there. It's gone from a secondary carbon to a tertiary carbon. And the logical way to do this is to think about starting off here. That's the functional group. That's where the halide is. And if I want to make it go over to here, I have to include this carbon. This carbon has to get included because that's where the bromide ends up. The simplest way to include a neighbor is to make an alkene. That's the simplest functional group you have, in which the functional group can come off and you can put a double bond next to it, and depending upon what base you use, you can put that alkene wherever you want. So in this type of synthesis, you're going to have to eliminate. Do I want to use a small base or a large base in that particular context? Small. If you're happy with small, great, this is fun. It really is just putting it together. Small base because you want what product? You want Zaitsev, you want Hofmann? You want Zaitsev in this case, so a small base is appropriate. Then we do the addition reaction. I want to put the bromine back on the other end in a different way to change the regiochemical outcome. What do I use here? HBr or HBr peroxides? HBr, right? Is that Markovnikov or anti-Markovnikov? Markovnikov. So we picked things up, and those of us who are left and those of us who are doing well, I think we'll start to see this is kind of fun. There's your they are your two big jobs between now and next Monday, is to understand to elongate a chain is simply carbon-carbon bond forming reaction with an alkyne so far. Next semester, a lot more of that, but also a functional group in conversion, which is all the reactions you've been seeing for a while now. So let's think about how we do this. Depending upon where you want to put your leaving group, if you need to move your leaving group around, it typically will involve an alkene because that helps you bring in the neighbor. If the neighbor doesn't seem to be activated, you can activate it as an alkene. So we have two different systems here. We're starting off with the same secondary bromide. That's something that's been given, or you've been able to make that. And in one synthesis, you have to make the tertiary bromide. And in the second synthesis, you have to make the primary bromide. So this is all about regiochemistry. There isn't really any stereochemistry here because there are no chiral centers, but in terms of regiochemistry, you have to understand the outcomes. So as we just said, small base will take off this HBr and make the Zaitsev outcome. And if we add HBr through a positive carbocation-driven mechanism, we'll end up with the tertiary bromide. So you think about next week and think about what we've been doing. Give me the mechanism of this process. Hopefully by now you're starting to see not just a bunch of letters and a bunch of symbols, you're starting to see some principles. I get that product because I went through the tertiary cation. That's your mechanism. There we go. If we want to go back to the starter material, let's say we screw up and we want this back. Well, I want to put the bromide back in the opposite sense, which is anti-Markovnikov. Then I can do that quite easily by adding HBr with peroxides, and that gives me the secondary bromide back. Now, in a different context, we maybe want to put the alkene here. What's the driving force? What's the principle behind using this Kottbu to be able to do that? Steric, right? The size of this base. The size of this base. It will have a hard time taking off that proton because it seems to be on a tertiary crowded carbon, and it should have a much easier time taking off this, which seems to be on a primary carbon, to give us the lesser substituted product. Maybe it's not the most stable product, but this is not a thermodynamic process because it's not reversible. And then we do the HBr peroxides, and that gives us the anti-Markovnikov outcome. Those are the types of things that you'll see starting next week. You know, I've already given you questions on the last exam where it was 2 or 3 steps. Next week, maybe 3 or 4 steps, so that we really have an idea of what we understand. Well, the basic principles here are tied together. The nice thing about this subject is once you understand the basics, you just add a few more details each term. In this example, we talked about Zaitsev versus Hofmann, or we talked about Markovnikov versus anti-Markovnikov. The vast majority of you who are getting through here and who will do okay next week understand those ideas. Think about something I said on Friday, okay? Or Monday, whenever it was. I want you to understand what the definitions mean. What is regioselectivity? What is stereochemistry? What is the idea of forming the racemic mixtures, stuff like that, right? You need to understand these outcomes so that you can define some things next week. Well, we can do different things with different starter materials. Depending upon what the planet gives you, depending upon what you can dig up or what a plant can give you, we can start to manipulate alcohols. If you think about 3720, the biggest, most important functional group in 3720 is the alcohol. It is central to everything else. If you can make an alcohol, you can go an awful lot. You can do an awful lot of chemistry. So we can do similar things here. In this example, we want to turn the secondary OH group into a tertiary alcohol. We have to move them. So you could do some bromide chemistry and replace it with an OH at the end, but alcohols have their own chemistry that avoid that. If you think about what's happening here, we are taking OH, and we are activating it. You could imagine taking this tosyl chloride, which was a big sulfur group, and it made the O a better leaving group because when it breaks off, it's resonance stabilized. And you could imagine doing maybe E1 chemistry here. You could add an acid and go straight from here to here. But what's the problem with those eliminations and those one reactions? When they form carbocations, what's the problem with them? They can rearrange, right? So if you're in a more complex system, you've always got to be wary of the fact that it could rearrange, and that can be a problem. So what's happening up here instead is sort of a nod to the idea that E2 chemistry is more reliable. You have more control over an E2 reaction than you do over an E1 reaction. So in this case, we're looking to form a good leaving group, the tosylate, and then we're bringing in a small base to do Zaitsev chemistry and to put the alkene where we want it to go. So just a general idea, you have to understand SN1 chemistry because it's very important in biology later, biochemistry, but the E2 chemistry here is much more reliable because you can put the double bond where you want it to go, you don't get carbocations, you don't get rearrangements. So what's happened here is a Zaitsev elimination by activating the OH group as a tosylate and then doing the E2. And finally, we need to put the OH group back on the other carbon. So what's driving this? Is it size? Is it polarity? Is it carbocations? What's driving that reaction? What type of mechanism is involved when you take an alkene and you add H3O+? Carbocations, right? So you want, again, the better tertiary carbocation, which then gets trapped by OH and gives you the outcome right there. There's nothing new here. It's nothing sort of mysterious. It's just putting it together to try and get to different products. I'm going to ignore the middle stuff for the second. What we need to do down here is to put the OH group on the other carbon. We want to put it on this one, the primary carbon at the end. I can't do that through Zaitsev chemistry because that's the wrong outcome. That would give me the double bond at the top. So what I need to do here again maybe is to activate this thing as a tosylate, which is fairly straightforward. Go back and remember what that reagent is. And then I switch my base. I haven't switched the mechanism necessarily. It's still an E2. But I've changed something about the environment that allows for a change in the regiochemistry. And what is it about this thing down here versus the one at the top that changes things? The size of it, right? The size of it. So then when you get transition states involving deprotonation, one will be a lot less energetic than the other because we've got problems hitting this proton, but we don't have any problems hitting the proton over here. Fair enough? Pretty straightforward stuff we've been hopefully testing you on and hopefully you're picking up. Now, just to think about adding those phrases again. Think about Markovnikov, anti-Markovnikov, Zaitsev, and Hoffman. Yes, you need to understand the definitions because they'll be important next term as well. Going backwards, let's say you did this and, it was Monday morning, you've just had Thanksgiving off, you're not awake yet, and you took the wrong bottle of stuff and you mixed it all together and then crap. And you've just used up 4,000 gallons of this stuff, but you wanted to go in this direction instead. And your boss is playing golf, right? As they do. And by the afternoon, you have to fix this. You have to make up for your error. So we've made this stuff, but we don't want this stuff. We want to go down here instead. You need to have methods to go backwards, not just because you screw up, but because often you'll be given this starter material and you have to go in the opposite direction. So go in the opposite direction then employs some of the other reactions we saw. I want to put the hydroxyl onto the secondary carbon. So I want to put it onto the less crowded carbon, which means I choose the B. BH3, or in our case, the parachute, and that gives you the opposite regiochemistry because you put the boron onto the less crowded carbon. So we now have methods to go in either direction. You go back to those few slides I showed you with everything together. That's what this is. It's just laying it out in the individual cases. So if you want to go into the anti-Markovnikov case and you want to go in this direction, you need to go back to this, and then you're going to need to go down to here. But look what's happened in this picture. Bigger picture idea. You've now got methods to involve all three carbons of that system. And in fact, if the problem required you to, you could go further. You could put a double bond over here if you wanted to between this carbon and this one. What would you have to do to get there? Would you have to use a big base or a small base? A big base, right? You'd want to do the Hofmann elimination to put it on the lesser substituted alkene. So you can start to make these molecules dance. You can move these things around quite easily and start to include carbons that are quite distant away from each other just by doing alkene addition, alkene elimination type chemistry. Once you see it, it's elegant. So other examples to show you the commonalities here. Once you've picked up the basic toolkit, it's pretty straightforward to put it together. Starting with this material, we have a alkene which is biased. In other words, one carbon is more crowded than the other, or one carbon could produce a better carbocation than the other, and so we have regiochemical problems. If we want to go to this bromide, is it through carbocations or radicals? Carbocations. You want the tertiary carbocation, you want the bromine to go to the more stable carbocation. And then we could think about going to the outside of this cycle. In general, the outside double bonds are less stable than the inside double bonds. In this case, it's obvious because it's di-substituted versus tri-substituted. So if I want to make this stuff, and I want the double bond to go where I want it to, I need to do E2. E1 won't give me that outcome. E1 would give me the double bond in the cycle. That's not what I want. So I need to think about using that large base again, and that gives me that isomer. Thinking about going in the bottom direction. If I want to put the bromine here, now, we'll pause for a second and think about this molecule. Any chiral centers up here at the top? Any issues of stereochemistry? You know, you think about the way I ask questions now. You've had 3 exams from me and a bunch of quizzes. I want to know about stereochemical issues. What does that mean? It means do I induce stereochemistry? Do I get double bonds that are cis or trans? Do I get R or S, or do I get mixtures which are then racemic? Those are the issues we have to worry about for quizzes and exams. So down here, do I get any stereochemical problems? Do I get anything that's interesting? Do I need any squiggles or any dashes or any wedges? Any ideas? What shape is that alkene? Flat. So give me a word that describes it if it can become chiral. It's prochiral. So if I add the Br first, I can add from top or bottom of that alkene, so I can draw a squiggle. You'll get a mixture of radical intermediates in which the bromine is either up or the bromine is down, because you can add to both sides. Well, that radical itself, once you've produced it, will be here. What shape will it be, roughly? Flat. So if you add the H in the next step, it can add from both sides, right? So how many isomers can I get from this process? I can get all 4 of them, because I can add top or bottom in the first step and top or bottom in the second step. So you've got to be careful now. This doesn't show it on this slide, but again, we are adding things together, and you should see now that you get all 4 of them. So at the end of that, the job now is to put the alkene there. Shouldn't be a problem here in terms of any anti-periplanar or syncoplanar stuff, because we're taking protons off this guy over here, and I'm using a large base again to drive the Hofmann outcome, and that gives me the double bond in the lesser substituted place. It's all the same problem so far. You just have to see that. Everybody okay? Yes? Thanksgiving was good? All right. So, this whole idea now of bringing it together, talking about the basic reactions, the simple reactions we've developed step by step along the way, and now using it to play a game. Those ideas of regiochemistry, those ideas of stereochemistry must be in there for this to make any sense. So here's what you'll see next week. For sure, this type of problem. The question will ask you, give me this product from this starter material. Make this from this. So I need to make the molecule on the right from the molecule on the left. What's the very first thing you would do? Count the carbons. I think I can see over here 1, 2, 3, 4, 5, 6, 7, yes? On the right-hand side, I see 1, 2, 3, 4, 5, 6, 7. I don't need to do any alkyne chemistry necessarily because I have the same number on both sides. I don't need to knit anything together. Well, when you see an alkene, what sort of reactions are we thinking of? What sort of chemistry could we use if, and be careful here, if we have an alkene that has protons or hydrogens next to the alkene here and here? Give me some ideas of what we can do with that double bond. Thinking about your quiz this week, it's all about 11. We can do some radical chemistry, right? And what is special about this position here? Give me a word that describes this position next to a double bond. Allylic. It is allylic. So maybe we could do some allylic chemistry. Maybe we could use MBS and heat this stuff up and get a controlled bromination at the allylic position. Or I could get rid of the double bond. And what do I need to do to get rid of a double bond? I need to do some hydrogenation chemistry, right? I don't need to worry about Lindlar or sodium ammonia because it's not an alkyne. I just need to add H2 and something else. So if we were to do something like this, You could do some allylic bromination, but you're looking for synthesis that is efficient. And what's the problem with the allylic system? If I try to brominate here, what will also happen? It will brominate here because we have resonance in the intermediate and you're going to get both halides. That's not efficient. That means separations. That means loss of yield. That could be a problem. So if I'm thinking about doing this, maybe I want to do some manipulations. Maybe I want to think about doing what we just did. Move the double bond around. How do I move a double bond around? I functionalize it as a halide and then I choose the appropriate base to get that double bond moved. So at the top, for example, what's the product of the first step? Is it Markovnikov or anti-Markovnikov? Anti. So where did the bromine go? Carbon 1 here or carbon 2 here? Carbon 1, the bromine goes there. Absolutely. And now, what I'm trying to do is to get this N carbon involved, because that's where the new bromine has to go. So do I want a large base or a small base? Large base, because I want to induce the Hofmann outcome, and that's exactly what will happen. So my molecule will then end up, or my double bond will then end up here, and finally I want to put my bromine at the end. If I want to put my bromine here, I'd probably, we'd probably use something different, but in this case I want to use the large base because I want to put the bromine on the less crowded carbon. Okay? I want to use peroxides. So those sorts of ideas now are adding up. What is different here? Number of steps. We've gone from a simple 2-step or maybe 3 from the earlier stuff, and now we're moving into 3 or 4 steps, which is more challenging. So to do this reaction, to do this synthesis, add HBr with peroxides. That gives you a racemic mixture of the 2 bromides. Add the T-butoxide. That gives you the double bond down at the bottom here because we've taken off a proton from the less crowded carbon. And then finally, add HBr back using peroxides because that puts the bromine in the right place. Everybody okay with that? See, Thanksgiving's in the wrong place, isn't it? So it should be in July. Everybody they take that exam, they get turkey inside themselves, give me the holidays. All right? And this is such a sort of, stamina thing now to get through this. So, there are other ways to do this. Let me say this again. Your synthesis might not be the same exactly as my synthesis, but it could just work just as well. There are many different ways of doing the same thing here because we have many different reagents. So, in order to do this again, we have the possibility of doing addition elimination chemistry through a different route. We could start off with the alkene and we could add the parachute and the boron will go here. And then when I add the peroxides, the OH will go there also. And that's trying to set up the same idea of moving this double bond around as I need to. The whole point now is to use tosyl chloride to activate that hydroxyl group and then to eliminate it using potassium T-butoxide. There's nothing different here in terms of the planning, in terms of the regiochemical necessities in the synthesis. We're just starting with a different material. Now, obviously, on the exam, I give you start with this, make this. It's usually clear-cut what you have to do. And then at the bottom again. Now, you've got, in the first reaction, you've got 3 steps, and in the bottom reaction, you've got 5 steps. Which do you think is more efficient, probably? The one with the 3, right? The fewer steps probably will be the better process. But at this stage of your careers, you are not experts in this yet. Either of them will be fine. Either of them get you where you want to be. Okay? All right, moving along. Now, you'll have to start worrying about several things next week on this final. It's comprehensive. It's 200 points. Read the questions carefully, especially on quizzes. Too many people are missing points because they don't read the question thoroughly. And they're in a quiz, they've got 20 minutes, they're done in 10 minutes, and they leave. And they lose 5 or 6 points because they didn't read the question thoroughly. Give all the products from each step. Okay? It might say give the major products from each step. If it says major, don't give me the minor. It saves you time. On a quiz, if it says give products from each step, and you have step 1 and step 2, please, I will say this in my nicest English, please give me products from step 1 and step 2. Because if you just give me products from step 2, I can't give you points for products from step 1 if you didn't give them to me. See what I'm saying? Be thorough. Read what you're doing. So all of this stuff now, 1, 2, 3, 4, 5 steps. That's probably it for next week. 5 steps. You do 5 steps, great. We've gotten someplace and we're happy. So then we start to bring in the second big job to do. We do manipulations using functional groups and we add things together. We do carbon-carbon bond forming reactions in which we add the pieces together. And the only way you have to do this so far really is alkyne chemistry. So we're keeping it simple. Next semester you'll have 15 different ways of doing this. Right now we're using alkyne chemistry. So looking at the product here, it is obvious that this one is bigger than this one. The alkyne has 7 on the right, it has 4 on the left. So you just simply have to think about the number of carbons that are missing and bring them in appropriately. And the only way you can do this that you know is to use this as the nucleophile by taking off a proton from the one end of the alkyne and using this as the electrophile. So what do you think X will be here? Bromine, tosylate, iodide, something like that. Something we can make quite easily, and similar things that you've made in the lab. We're going to do simple chemistry by adding the 2 pieces together. What's the mechanism for this process? When this guy goes after this and it kicks this out. What is that? That's an SN2. Very good. Okay. Conversely, the only way, this is an important slide that you want to make a note of, for those of you who are awake, you add carbons together through alkyne chemistry, and you can break carbons apart using ozonolysis. Ozonolysis, lysing things, breaking things apart. This is really the only way we had to do that. You can start doing ozonolysis chemistry, and that will break this double bond here and replace the double bonds with oxygens. So you can go to a smaller molecule by ozonolysis, a bigger molecule like alkyne chemistry. That's really it in terms of chain extension or chain degradation. And then we start using this. We'll just practice a whole bunch of things between now and the end of the, we'll just carry on. We'll start to do some planning in a second when we have to think backwards, but we just put it into practice. Do I need a carbon-carbon bond extension or not? How many carbons do I need to bring in? 2. Don't forget with these alkynes, that's a carbon and that's a carbon. They must count. So I've got, I think, 5 over here, 7 over here, I need to bring 2 in. Can I go directly in one step from this molecule to this molecule? No, of course not. What's the first operation you should carry out? Acid-base reaction, take that proton off. What's an appropriate base to do that? NH2, absolutely. And then what's the next step? Do I reduce? Because I need to make an alkene. What do I do next? Bring in the electrophile to extend the chain. So I'll start doing this type of stuff. I've done my counting, and I need to start thinking about where it's going. What's the clue here? What type of alkene am I making? Trans. So what do I need to use? Sodium ammonia or Lindlar? Sodium ammonia. Make notes, right? Jot things down. The problem with the last exam, not for most of you, but for a few people, you leave blank space, I can't give you anything. Yeah? I mean, a few of you invoke the 1-point banana rule, and that's fine. You get to use it once. But on the final, write stuff down so I can give you as much as we possibly can, because the grades are still quite fluid. So here's what we'll do. We'll take that starter material. We'll deprotonate with a powerful base. If you choose the wrong base, we're in trouble because it won't work. If I use hydroxide here, will it work? No, it's not strong enough. What's the pK of the conjugate acid of hydroxide? 16. What's the pK of the conjugate acid of NH2 minus? 38, right? Definite difference there. What's the pK of an alkyne? 25, 26. You need the more powerful base to make this work and make it go to the right-hand side. So once I've done that in my first operation, I have a product, which you must draw. And then I add into the flask ethyl iodide very carefully. And I get my subsequent SN2 reaction, and away we go. We get the alkyne product. But the product we want is an alkene. So finally, in the last step, you have to reduce. It seems fairly obvious when you see it in front of you like this, in a sort of a stepwise, careful, considered way. But when you see a molecule for the first time, the biggest problem people will have is when to do what. So my advice is, write the steps down on the side of the paper. Write down, at some point, I need to do sodium ammonia. At some point, I need to do NH2. At some point, I need ethyl iodide. Write that down, and then think about the steps. Because if you get the steps wrong, obviously, it's not going to work. Moving into the big world. Okay, as far as I'm concerned, 3719 is done. We're getting people who are passing, people who are struggling. That's the way it is. 3720 is all about going bigger. It's all about getting to bigger molecules, to things like biology, things like polymers that people are interested in. How on earth do people, scientists, human beings, decide on a molecule like this, brevetoxin B? How on earth can they look at that molecule, which was given to us by nature, and they want to make it? They want to build it from small molecules. They have this Lego kit in the lab. They've got all these little yellow bricks and red bricks and blue bricks, and they want to build the Taj Mahal, right? They want to put it together, so this is the same sort of thing. How do you do this? You don't just start slapping bricks together, because that doesn't work. That's my neighbors, okay? You need to plan, I need a yellow brick here, I need a red brick here. They need to go together to give me something. Then I need to build off of that with something else. And I need to build off of something else. Now you can, if you want, start with something arbitrary and just go at it, right? You ever see little kids playing with these things? Buh, 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 buh. They just throw them together and at the end of the day, look what I made. Okay, looks cute, but it doesn't do anything. It's not functional. When we get to our stage, we need to be thinking about function. If you start doing random things in the lab, you'll get maybe 2 or 3 steps, and you'll be like, oh crap, that's not going to work, and you go backwards. And then you get to 4 steps, it's like, oh, it's not going to work, you go backwards. Now you could do that, it'd be a waste of time, waste of material, a waste of people hours, or you could plan it. And this little arrow here, you haven't seen this one yet, but this will keep you up at night, this will keep you awake. This new arrow is a method that's been devised to help you plan a synthesis of a target. And this is called retrosynthesis. This is thinking backwards. This is looking at what I need to make, which is over here, and knowing I have a bottle of this stuff over here, and they're separated by 4 or 5 different intermediate compounds. Or in this case, 146 intermediate compounds. This is now well developed. There are computer algorithms out there that will help you do this in a complex sense. If you start off with this, it takes 147 steps to get back to those 2 materials. Okay? So the planning that went into this is absolutely world class. This is some of the best thinking on the planet. How do you go back to that material? Well, you take it stepwise. You look at the product and say, okay, I can take this back by taking off that bromine because I know how to put the bromine in. I can then take that alkene back to an alkyne because I know how to make an alkyne. And you're starting to think like a designer. You're starting to design the synthesis. Obviously, 147 steps is not going to work for us, but these chemists came back with this compound, 2-deoxyribose. Everybody knows where that comes from, right? DNA. You can get lots of it. And D-mannose, which is a common carbohydrate. And they start off with this material. Having done the planning backwards, they then start the chemistry forwards. And in any type of synthesis like this, you hit a roadblock. You'll get to a point where you're 10 steps in. Ah, crap. My designed synthesis isn't going to work. Then what you say is, okay, do I go back to the square one, or do I work around? And that's where we invent new chemistry, is working around. I'm 10 steps in. I don't want to go 10 steps back to go 10 steps forward again. I want to design a new reaction that gets me around to step 11. That's where new chemistry comes from, a lot of the time. So this is a lot of hours. To make that molecule costs something like 150 years of people time. Right? That's dozens of scientists working weeks and weeks and months and years. It took 150 odd years to make this thing in terms of people time. That's how intense this stuff is. Obviously, we're not going to get there. At least not this semester. What we are going to do is start thinking about the relationships between different molecules in the reverse sense. It's not an equilibrium sense, but what do I know to get this molecule? How can I think backwards to give me this product? This is very different. This is nothing, you can't memorize this stuff. It's a skill. And it'll test whether you can think or not. You're given this starter material, and you need to make this alkyne. Or the other way around. And it's the right direction. And we need to start thinking about, how do we do this? How do we design this thing? And it really is analogous to building a house. If you build a house, you have some idea of where you want the roof, right? The roof typically goes on top. Are you listening, Haldeman? The roof goes on top, the basement goes underneath. Yeah? The kitchen is usually on the first floor, and the garage is next to it. This is just a simple design, right? You know where things need to go. When you're trying to design something from scratch, you've got to have an idea of where you want to be. This is the molecule we want to make. We need to introduce functionalities. We need to worry about, do I need to do any carbon-carbon bond forming reactions? I don't think we do here because I have the same number of carbons at the start and the beginning. So we're going to say, this is where we start, and this is where we want to be. Okay? And we're going to start worrying about, how do I make alkynes? How do you make alkynes? What type of chemistry is required to make a triple bond? Eliminations, right? How many eliminations? 2. Those who do well on quizzes and on the homeworks here, you can see this stuff now. This is why we're doing it. 2 eliminations will make you an alkyne. But what is that thing that eliminates to give you that alkyne? What things do we need to eliminate to get out, to take out of this molecule? This molecule here is going to be something we need to make to take things out of it to make an alkyne. But what are those things that we take out? Halides. Halides, right? What's the simplest way, since I need to do 2 eliminations, I need to put 2 halides in. What's the simplest way of putting 2 halides in? Add Br2. Okay, add Br2. So what does Br2 add to? Alkenes. Then we're back to the middle here, right? And how do you make alkenes? By eliminations. So now we can start to put things together. This is not simple. You might not get it by next week. You'll have to get it next term. There's a whole chapter on this stuff next term. Retrosynthetic analysis to be able to build a complex molecule. So we need to make some kind of halide. dihalide to give us this. From what we've seen so far, I don't know how easy it is to make that, putting them both on the same carbon. I don't know how easy it is to make that, putting it both on the same carbon, but you have done this one, where you put two bromines on adjacent carbons. That's pretty straightforward because the precursor to that is an alkene. So having decided to do that, we know our alkyne can come from this bromide. We then have to go a step further back. Where does the dibromide come from? Well, we've already said just now that we need to put leaving group on here and leaving group on here, so we need to add something. What do you add to? You add two alkenes. So the precursor to dibromide is the alkene. Now, how do you make alkenes? Eliminations. That's it, eliminations. So if I need to eliminate, the molecule that comes next in our thinking backwards is what? It's a bromide or it's a tosylate. So we can start to do this. We can start to think about the alkyne is what we want. That needs to come from a dibromide. That can come from an alkene. Where does the alkene come from? Well, the alkene, all of a sudden, we can start to think about coming from elimination chemistry. So we've put the steps together. How do we turn this guy, how do we turn this guy into this guy? What do I need to do to the OH group? Make it a good leaving group. Now, is H3O plus a good idea here? These are the types of questions I'll ask on the final to make sure we understand. Why is H3O plus not a good idea here? It's a primary system, so carbocations won't be too great. And if you were able to put the double bond in there, what can happen to a double bond in the presence of acid? It can add, right? And maybe it adds in the other direction in the Markovnikov sense. And then we get a carbocation rearrangement. It gets messy. So maybe we do this. Maybe we activate it through the tosyl group. You take the alcohol, you put in the tosyl chloride and the pyridine, and that gives us the tosylate, because now we can do a controlled reaction. We're not concerned about carbocations rearranging because there won't be any. You're making a tosylate, it's a good leaving group, and then we're choosing this. Why choose this? It won't do SN2. Absolutely. You don't really care about regioselectivity here because you've only got these two carbons to worry about, but this guy will not do an SN2 reaction. At the end of that, we get the alkene, then we do what you did in lab, which is add bromine to the alkene, you make the dibromide, and all of a sudden we're getting close. So I've got 1, 2, 3, 4 steps, and we've designed it in such a way that it's logical and it gives you high yields. You can't just throw stuff in here. You can't just say, okay, I'm going to throw some H3O plus in because that gives you a mess. So you need to really be on top of what you're doing with the chemistry to be able to put it together. This is the synthesis. This is the retrosynthesis. There's that arrow again. Where does this come from? It comes from here. Where does this come from? It comes from here. If you know the reactions in the forward direction, all we're doing is tweaking the idea a little bit. So you can start to plan. What's the best way to get good at this? Practice. Just practice. Do as much as you can. So there are your viable steps. Jacob. Yeah, now let's tidy that up while we're here. When you add this stuff, it's a powerful base, yes? And we could argue maybe this comes off first, and we eliminate, and we get a double bond here, and that double bond still has 1 bromine left. And then we eliminate again with a second molecule of NaNH2. And that gives me this guy at the top. But I now have that hydrogen there. What's the problem with that hydrogen? I'm in the presence of a very powerful base, so what's the problem with this H? It will get deprotonated. So as soon as you make some of this stuff, any of this available will deprotonate it. So the actual product from that first step is not the molecule with the H attached, it's the negative charge. A lot more of that next term, worrying about the environment. What did I just make? What environment am I in? Can I go someplace else? In this case, yes, you can. So that water there is to quench. We haven't used that word yet, this term, to quench, add an acid, neutralize your product, and give the proton back. That's what that's about. Ashley. You can do that, yeah. You can do HBr, add HBr a couple of times, HBr peroxides. That's a bit more messy, and the one we just did was pretty straightforward. Okay? So, not thinking about just the final, but thinking about next term, we're now building up complexity. There is a sequence next term in which you have 11 steps to worry about. You start off with ethanol, you end up with something very complicated through 11 different steps, one after the other. This term we'll do 4 or 5 at the end, but next term obviously builds up. There is a problem set which has 37 steps in it. Now, if you like this stuff and you're starting to get it, it's great. It's just challenging you to do a bit more, you know, become a bit more confident in what you're doing. There's not much to it. So, thinking about going there. You can now start to add these things together to go different places. We can start to add different parts of different reactions, different molecules to different systems to get quite complex products. What we're trying to do here is to think about turning this into this. There isn't much difference, but look how many steps it took. There's not an awful lot of difference between the starting material and the product. And it's not simply moving a double bond around. I've got 2 carbons outside the cycle here. I've got 3 carbons outside the cycle there. And if you're sitting there saying, so what? Well, you know, maybe science isn't for you. But if you're sitting there going, all right, it's a problem. It's a little puzzle. How do I solve the puzzle? Because you know the answers. You know the chemistry. You just have to put it together. Well, I need to extend this chain somehow. And the problem is I can't put an alkyne here. Why can't I put an alkyne there? I obviously need to make an alkyne to extend the chain, but why can't it go there? You break octet rules. You can't put 3 carbons on an alkyne. You can only have 2, so that end doesn't work. So somehow I have to functionalize this end of the molecule to get that guy involved. Why not just simply throw in some NBS and do some radical halogenation? Resonance is an issue because it will give you different products. It will give you mixtures. Maybe the one you want isn't the one that's major. So this series here of anti-Markovnikov addition of HBr, to put the bromine here, brings in this carbon. Because if you have a leaving group next to it, you can eliminate using a large base and put the double bond where you want it to, which is there. Once you've got a double bond there, you can start doing the bromination chemistry to make the alkyne. Then you can start doing the elimination. I'm sorry, you can do deprotonation, then you can do alkylation, and then you can reduce down because in this case you need the transalkene. I'm not going to ask you 8 steps next week. I'll save that for 3720, but certainly 5 are on the board there. Okay. You practice. A lot of stuff out there. A lot of stuff in the book, a lot of Orion problems, quiz problems, homework problems, stuff on my website. Just practice. Knowing that there are no new reactions in this chapter. It's all stuff you've seen. Okay, give me some ideas of what has to happen here. Need to use an alkyne of some sort. You need to do some carbon-carbon bond forming chemistry. You need to do some alkylation chemistry. What size chain do I need to bring in? 3. Okay, so what do we do first? Do I reduce first? Do I go for the double bond first, or what? Take this guy off, take the proton off. What do I use? NaNH2. Then what do I bring in? Give me a name of a molecule. Propyl bromide. That works well. After that, you get an alkyl chain over here. You have an alkyne over here. Then what do you do? How do you get the alkyne to become a double bond, which is trans? Sodium ammonia. Sodium ammonia. Okay. Now, you know, we've built a toolkit, but we haven't used all the Lego bricks. We've used the red ones and the yellow ones and the blue ones. But next semester we get the black ones, the purple ones, the orange ones, the turquoise ones, everything else. We've got a simple kit right now, the starter kit. There are only so many reactions you can do. There's only one way to take a chain smaller, ozone. There's only one way to take a chain bigger, alkyne chemistry. Have a go at this stuff. If you can do this, you're in great shape. We deprotonate in the first step. We make this as a nucleophile. We add this as the electrophile. We make the alkyne. We reduce it down. You will find, most of you, this term, that you don't need to think backwards, and you will struggle to think backwards. You'll find it pretty straightforward for those of you who've been keeping up and doing well to go in the forwards direction only. I won't ask you to design the synthesis backwards. That's next term. You'll be able to go forwards without any problem. This technique of retrosynthesis becomes really important when you have 5, 6, 7, 8, 9, 10 steps. And you just can't do it randomly. You have to think about planning. Have a go at it. If you don't get it, don't sweat, because we'll do more of it next year. What has to happen here? What sort of things come into your head, apart from turkey? Chain elongation, including carbon-carbon bond forming reaction using an alkyne. This is not an alkyne. I need to turn it into an alkyne. So what sort of chemistry should I do to do that? You could add HBr, or you could add what? You need a double elimination. So what's the logical thing to add to an alkene to make a double elimination happen? Br2. Put a couple of bromines on, then eliminate. Then you get your alkyne. Then you deprotonate, and then you can do... Let's do that, okay? Add 2 bromines. Simple elimination to get to this. Second step again is to protonate to give the proton back. Then deprotonate, that's after we've isolated this stuff, get to this anion, alkylate, and that's your product. I'll say it again, there are only so many permutations of this year. There are only so many ways you can do this term. Whoa, look at that. That's kind of messy. Any ideas? How do you make a diol? First of all, is it a cis or a trans diol? Trans. How do you make a trans diol? What sort of species do you need to make a trans diol? An epoxide. Jot these things down. Even if you're totally lost, jot some stuff down. Practice. If you want to come to the office now, so we can do problems again. I needed to make an epoxide. But look at my starter material. Does my starter material have any functional groups at all? No, it does not. What's the simplest way to functionalize that material? Radical what? Bromination, right? So I want to put a bromine on there to give it a handle to be able to work with. What's the thing I need to make before the epoxide to put the epoxide on there? Alkene. Now we're thinking. So I've got now thinking, all right, here I'm thinking epoxide, because that gives me the anti-setup. Epoxides come from double bonds. I'm writing this down. I'm doing retrosynthesis, just writing it down. These guys come from halides. Okay? So I need to put a halide on here, need to eliminate it to make the alkene, need to epoxidize, and then what's the last reagent to open an epoxide to give the anti-stereochemistry? Acid, yeah, good. So there we go. We are making stuff. Br2 and heat gives you the bromide. Why is the bromine going there and not elsewhere? More substituted radical, yes? To give the more substituted product. Why use a small base here? You want the Zaitsev outcome. You want the double bond to go where you want to put it. And then we can do an MCPBA reaction or a peroxyacetic acid, put the epoxide right there, and then I add acid and away we go. It's fun. It's very, very versatile. It's very, very useful. Now, I'm going to stop there. We'll do some more on Wednesday. And that's all we're going to do for the week. Is practice.